So we're going to take a look at two nucleophiles, and we're going to reference section 7.3.2 in our Top Hat textbook, where we're talking about nucleophilicity, so nucleophiles, and solvents. So how nucleophiles will behave in different solvents. So first, let's just look at what we have here and what's the difference between what we have. We have a small, or O minus, and an S minus. So what's the difference between O minus and S minus? S is bigger, size, right? So size is the difference here, with the sulfur being larger. Excellent. So we got to think about that. That's going to be the important factor when we think about solvents and how that's affected. So there's two types of solvents we talked about. Well, there's three types. There's mostly we talked about polar solvents. A lot of these solvents are polar. We've talked about protic. We talked about aprotic. Protic solvents have hydrogens bonded to heteroatoms. Aprotic solvents don't, but they still have polar bonds. So things like acetone, DMF. These are polar aprotic solvents. One thing you want to notice here, these heteroatoms can do hydrogen bonding, right? So they're really, that's the thing we've talked about before. We're just calling it polar protic solvents now. So we got to think about, in these two different types of solvents, how are these solvents going to affect the reactivity of these nucleophiles? So the key here is, essentially polar protic solvents are going to react or interact with our nucleophiles, especially if they're charged. And that's bad, because we want our nucleophiles to be reactive. We don't want our nucleophiles interacting with the solvent. We want our nucleophiles interacting with the electrophile. Right? Whether, in this case, especially whether it's E2 or Sn2, whatever one we're doing, we don't want this messing with the solvents. So which one of these types of solvents is going to interact or react most with these nucleophiles? It's going to be the protic ones. The protic solvents, right, because they can do that hydrogen bonding, they have that polar OH, NH, pH, SH bond, is going to interact most likely with the solvent. Now let's think about how that matters as far as size goes. So, right, we can both look at these and say, oh, both those are charged. They're definitely going to enter the solvent. But there's a difference between these, and that's the size, the first thing we talked about. So how does that play a role in this? Let's maybe draw a picture. So I'm going to say that's my oxygen. It's electron cloud, as it were. And that's my sulfur. Sulfur's bigger. This is a crude picture. Essentially, what you need to think about is, if you're larger in a protic solvent, right, in a larger atom in a protic solvent, it's going to be tougher for this polar protic solvent to surround this and prevent it from reacting. Whereas a smaller atom in a polar protic solvent is going to be much more easily surrounded and prevented from reacting. That's going to slow the rate down. So as a result of that, so if this is the smaller atoms and the polar protic is more easily surrounded, that's going to make this less reactive in a protic solvent. Which means it's a less reactive nucleophile. Right? Which means a less reactive nucleophile. Or a weaker nucleophile. Whereas the larger one's going to be harder, right? Just imagine these solvent molecule, or the solvent molecules trying to surround it. It's going to be tougher. There's a great picture in our book. It's figure 7.14. Take a look at that for another different type of example, but the same. You'll see that picture there. It's great. Take a look at that picture, 7.14. So now if we're in a polar aprotic solvent, then the solvent's not messing with the nucleophile anymore. Then it's all about, right, reactivity. And that would mean the smaller things are more reactive than the larger things, right? The larger atoms can spread that charge out. So then then the solvent's not a factor anymore. So then it's just back to that normal idea about size. Something that's bigger is more stable, so something smaller would be more reactive. So in that case, in an aprotic, this would be more reactive. In an aprotic, we just go back to our idea about size. The bigger, more stable, means it's less reactive. Oxygen is smaller than sulfur, and an aprotic solvent, therefore, would be more reactive. Yep, so so doing some chair problems. I just made 2 cyclohexane rings. And then my numbering is arbitrary in this case. I didn't use it as naming. We obviously could name this if we wanted to, but my numbering here has nothing to do with naming. So just to help me translate from a flat wedge and hatch to a chair. Right, the idea being here, we need to practice these chair structures again because we need to think about especially E2 reactions. Right, when we talk about E2 reactions. Talking about E2 stuff. I mean, you can think about Sn2 stuff where you flip, right? We flip the stereochemistry as well, but especially E2 because we need to get things anti-coplanar or periplanar, which means you need your leaving group and your hydrogen 180 degrees apart. You get your leaving group and your hydrogen 180 degrees apart. So in chairs, you gotta be careful, which that means is your leaving group, whatever it is, needs to be axial. So now I got lucky here. I didn't try to do this, but you easily could have drawn this and had your bromine or chlorine axial, equatorial. And if that was the case, what do you need to do? You need to do the ring flip and draw the other ring version, the other conformation, to make sure the leaving group is axial. If you drew it equatorial, that's okay, it's not wrong. You just need to do the ring flip now to make sure it's axial. Make sure the leaving group, whatever it is axial. So do that right now. All right, so if you've done the flip, you got your leaving groups, both axial. Now you need to look for the beta sp3CHs, right? But now you gotta be careful because it can't just be any beta sp3CH. It needs to be the beta sp3CH that's 180 degrees away. That's anti-periplanar, anti-coplanar away. So in this case, in this one, there actually is only one beta hydrogen possible. Carbon 1, as I have it labeled, has 2 methyls on it. So if I use the base, let's say, that would be the E2 mechanism there. Taking that, right? See, it's 180 degrees apart. It's anti-coplanar. Taking that beta sp3CH. Down here, what should I do for a base? Let's do nitrogen. Which hydrogen am I going to take here now, though? It's a little trickier. There is a beta sp3CH on carbon 3, but that's not axial. It's not trans, right? So it has to be this one again on carbon 1. What do those products look like? You can draw them as flattened structures or as chair structures. I'll draw them as flat structures with wedges and hatches. So carbon 1 still has that. There's a pi bond. There's a methyl there. Whoops, that's that. Down here we'd have, let's see. And renumber everything. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So those are the 2 products you'd make. Notice, right, there's still wedges and hatches in some of these spots because they didn't change, right? That didn't affect, right? This reaction didn't alter that stereochemistry if there's anything there. Of course, this is not a stereogenic carbon, right? Because it's not bonded to 4 different things. This one is, right? This one is now. So just be careful with that. Numbering, good numbering system. Be able to do those chair flips. So always be careful. sp2 hybridized carbons do not have wedges and dashes. If you do that, that will be incorrect. They are flat. Right? They do not have, right? They're flat. sp2 hybridized carbons do not have wedges and dashes. No. So here's the situation. You have a pair of enantiomers. So these two are enantiomers. These are enantiomers to each other, pair of enantiomers. And you do a reaction, and all of a sudden what I had as enantiomers become diastereomers. So let's focus on this, these two pairs. So let's say we have a reaction that's going to take place on the one to the right. That's where our leaving group's at. That's where the stuff's at. What that means is this stereocenter is not involved with the reaction. It's just along for the ride. So what that means is if this stereocenter is R, and if it's S, nothing's changing. It's going to stay R, it's going to stay S. But what happened was the stereocenter that is reacting is the second one. So it was R here on this compound, and it was S here on this compound. We run the reaction, all of a sudden, we get 2 new compounds. We get an RS and an SR. What happened? So what was R became a mixture, right? Or actually, no, I take that back. What was R became S, what was S became R. So these are what to each other? What are the relationship of these two things to each other? They're enantiomers. So we started with enantiomers and we got enantiomers. What kind of reaction would that tell you? If one molecule went from R to S and then went from S to R, what kind of reaction would that tell you it was? Sn2. All right, so this first version would tell you it's Sn2. If you start with enantiomers and you get enantiomers out, right, that's Sn2. You inverted the stereochemistry on both of them, Sn2. Now, what happens? So in the one reaction scenario, we got just 2 things. What would happen if and I'm going to highlight, what if we got all 4 of these things? What would that tell you? That would tell you that the center that's reacting is becoming S and it's becoming R. It's becoming R and it's becoming S. What does that tell you? That tells you that it must be going through not inversion, but it must be going through a carbocation. So if you get racemization, right? Notice how the R stayed the same, the S stayed the same, because that was right. That's still the same place. It's not reacting. If all of a sudden you got a bunch more products, if you got diastereomers, right? Because that's what are these things to each other? These are diastereomers. One thing's the same, the other thing's different. So kind of across ways, they're diastereomers. And this way, they're enantiomers. But if you did an Sn2, you get enantiomers back out. If you did an Sn1, you're going to get diastereomers because you're going to get that racemization. So this is very similar to the substitution elimination reaction test exam from 2015. The second number 3. Similar type of question. This was part A. Tough question. Absolutely tough question.
So if it says like enantiomers become diastereomers, we're assuming the diastereomers 2
So these two.
It's assuming that all four are in.
Yes, yeah, they're all in there. Yep. So that there's an assumption there that you're assuming you started with at least 2 stereocenters, because I never could make diastereomers unless I started with 2 stereocenters. So that's why it's like a lot built into that question. All right, let's practice working on isolating variables: the nucleophile, the electrophile, the solvent, and the leaving group ability. So let's look at all those factors, and then we'll break down what kind of reaction we're going to do. So the first one, I have 2 things. I have 2 alkyl halides, 2 electrophiles. My question to you is, which one's going to react faster and why? So this one is going to react faster because iodine, right, is a better leaving group. Why is iodine a better leaving group? I minus versus Cl minus, right? So it's larger, it can spread its charge out more stable. Good. Okay, so let's go with that. That'll be our alkyl halide. So that was focusing on the leaving group. What factor should we go with now? Let's go with the type of alkyl halide. The type of alkyl halide. So what kind of alkyl halide do we have here? Or type of electrophile, right? So this is all about the leaving group. Now we're going to go to the electrophile. What kind of electrophile do we have here? Primary benzylic. Excellent. What type of reactions can work with primary benzylic? Can everybody?
Yes.
You need to have sp3CHs. Can E2? Do you see any beta hydrogens that are sp3 hybridized? Is there any beta sp3CHs here?
No.
There aren't any. So this is a primary benzylic. If there's no sp3 beta CHs, what does that immediately eliminate? Can we have E2 or E1? We cannot. Right? No sp3 beta hydrogens. Doesn't have any. Actually, either would primary allylic either. Now that I think about it. Right? Primary allylic can't do E1 or E2 either. There's no sp3 beta CHs. So that just narrowed it down between what? Sn2 and Sn1. So what have we narrowed it down to? Between Sn1 and Sn2, right? By looking at the alkyl halide. Okay, which one do we want to do? Do you want to do an Sn1 or Sn2? We'll do Sn1, or choose an Sn1. Or you can go with Sn1. What type of solvent should we use for an Sn1 reaction? A polar protic solvent. Good. Can you give me an example of a polar protic solvent? Water. Any alcohol, any amine, NH, right? This solvent, which is polar and protic, is also going to act as our nucleophile. It's also going to act as our nucleophile. Is this nucleophile reactive or unreactive? Water? Water's pretty stable. It certainly doesn't have a charge, and it's water. It's pretty stable. So that fits the bill for an Sn1 reaction. Right? So that's how we could break this down, right? So this is another, maybe a different way of looking at it, right? Start with something, what's more reactive? Look at the alkyl halide, okay, what's possible? And then if I ask you, I want you to do an E1 reaction. I want you to do an Sn1 reaction. Do you know what kind of solvent works best? Do you know an example, something that might work for that? Think about it that way too. To create your own problem as well. So let's actually do this reaction. So we have a primary benzylic electrophile. We have a weak solvent, protic solvent. This is going to be an Sn1 reaction. We can't do E1 and E2, we said, because there are no beta sp3CHs with this primary benzylic alkyl halide. So the first step is going to be the rate determining step, forming a carbocation. The RDS. And of course, this is okay. It's a primary carbocation, but it's primary and it is benzylic. I minus could certainly go back, but when something's below the arrow, that's kind of significant. That signifies it's the solvent. Right? So there's a lot more water around. So the water is actually going to act as my nucleophile because now this is my electrophile. So the water is going to come in. Lone pairs go there. Lone pairs of the oxygen. Did I break any OH bonds? Nope. Not yet. Nope. Maybe in a bit. We'll see. I need, of course, to balance my charge. Things I constantly see. People forget to put the plus charge on that oxygen. Plus charge. Balance that charge. Balance thy charges. Last step, we need to get the hydrogen, this hydrogen-oxygen bond broken. I can use the I minus, or I could use more water. Doesn't matter which one you want to do. It's all good. I'll use the I minus in this case. The final product then is benzyl alcohol. We've also made HI. And that's our final product for this Sn1 reaction. We could have also done an Sn2, but that would require changing the nucleophile and the solvent. More reactive nucleophile and a polar aprotic solvent would work better. So there's your Sn1 product. So good question. Why do we have to do this last step? Partly it's just to balance out the charge, and then you don't like to have your final product having a plus charge on it, right? In a mixture, these protons hydrogens are coming on and off of these heteroatoms, but usually it's just to finalize it. You'd like to just balance out the charge or use the solvent to take the hydrogen and then have whatever your actual important product would be, not have any charges. So it's just a matter of tradition, maybe even.